Okay. So let's resume where we stopped yesterday. Other questions on what we saw? A short recap. We started analyzing how to perform calibration. We said there are methods that we will not discuss that we can prove are give you a calibration transformation of the scores that can be shown to be optimal for the calibration set through a regression algorithm that I didn't explain what isotonic means. Essentially, it guarantees, it makes a fit, a regression, so fit of a curve that is monotonic. So it's the best monotonic fit to your scores. As I said, we are not going to discuss this. If you want, you can look, you have some information on the books and you can find online, but this is just to say, there exist methods that give you an optimal calibration on the training set. We said we are not going to use them because, first of all, we don't have the amount of time required to see them. And then there are some practical considerations that, again, I'm not going to ask you at the exam, but if we were to discuss these algorithms, we would see that there are some practical issues from the point of view of computational complexity. And therefore, we said, okay, let's try with something slightly different. Let's try to work on scores. So we discussed, okay, let's see why generative and discriminative methods fail in providing well-calibrated scores when applied to the feature vectors. And let's see what happens if I can use the information extracted from a validation set on the scores to compensate for the calibration error introduced by these models. We started with a generative model saying intuitively, if we have a knowledge on the distribution of the scores for the two classes, then we can use this information to try to understand how to compensate for miscalibration. One possible way that we saw is to use the information on the score, treat the score as if they were features, try to model the distribution of the scores, and use this model to compute a log likelihood ratio for the scores themselves. So the scores that are well calibrated represents a log likelihood ratio for the feature vectors. When the scores are not well calibrated, this is not true. Well, they represent a score that is not a well calibrated log likelihood ratio. Let's try to make a model for the score themselves so that the model for the scores can be used to compute a log likelihood ratio over the non-calibrated scores, and then use this as the new calibrated score. So we treat the scores as if they were same features, and then we make a model for the scores and use this model to compute a log likelihood ratio for that essentially these are densities, but if these were probabilities, is the probability that we observe a score for the class true over the probability that we observe the score for the other class. Now, the word probability is incorrect because these are densities, these are continuous, but to get an intuition of what we are trying to do, you can reason in this way. So we said one possible way, use a generative model. Then an alternative way is fix the calibration transformation and use a discriminative method to learn the transformation. So assume that the transformation is, for example, an affine transformation, then assume that this must represent a log likelihood ratio, which gives also a form for the class posterior ratio. Now that we have an expression for the class posterior ratio, we can learn this by logistic regression and then recover our original transformation. The only thing that we need to pay attention is that we correctly compensate for the prior of the training set. And actually, rather than using prior of the training set, we will use the prior weighted model, so we fix the prior that we train for, and we don't use the standard logistic regression, we use the prior weighted logistic regression that we have seen a few weeks ago. Then we need to compensate for that prior. The result is a model that, given an uncalibrated score, this is the uncalibrated score, will give me a calibrated score as output. We said this works well when the linear transformation is a good approximation of the optimal calibration transformation that I would have if I were to evaluate the optimal calibration transformation on the evaluation set itself, the data that I want to classify. Now, we said that we need a calibration set. What should be the characteristics of this calibration set? Well, if we want low calibration error, obviously the calibration set should be similar to the evaluation set. And it should be different from the data that we used up to now. So the validation set, we said we will use a validation set to estimate the calibration transformation. Or originally we said we will use a validation set to estimate the optimal threshold. Typically using directly the validation set that we employed to compute the performance of the different models may lead to results that are slightly biased. Why? Because the matrix that we were computing on this validation set, we were optimizing the matrix for this validation set. All the hyperparameters we were tuning them for the validation set. So ideally, we would like the calibration set to be different from the validation set itself, which essentially means, let's skip a few slides, that ideally the optimal scenario is we have data to train the model, we have data to train the calibration transformation, and we have data to validate. And now here the validation will not be done with min DCF, but we will done with actual DCF because we are calibrating the scores, so we can finally validate the models using the metric that reflects what we will actually have in the real scenarios. I will come back to this in a moment. How should we select this calibration data? Well, we have essentially two sources of miscalibration. Typically, we have seen miscalibration due to models that have non-probabilistic scores, overfitting, underfitting. In this case, we can imagine that the training and evaluation populations are similar, so we assume that there is similarity between the data that we trained things on and the data we will apply our model on, and the sources of miscalibration are due to the characteristics of the classifier. Non-probabilistic scores, or the classifier is not adequate for the amount of samples that I have, or is not complex enough to model those samples. In this case, the calibration set is similar, the training set is similar to the evaluation set, so there is no risk in taking the calibration set out of the training set itself. So the typical use case is we will do as we have done up to now. We have our train set, some of the data will be taken out to train the calibration model. And as we said, the benefit, why this works? Well, because the source of miscalibration was coming from the characteristics of the classifier, or for overfitting and underfitting, which is typically due to I need to regularize to avoid overfitting, or my model is too simple, or I have overfitting because I have many more parameters, and we said yesterday that since calibration is trained only on scores, all these problems, well, first of all, we don't have the problem of non-probabilistic scores because we have a probabilistic model for the scores, so the result is a probabilistic interpretation. And then, since the model is simple and trained on, is a simple model, it's linear, it's trained over data that is low dimensional, one dimension, we have only one score, then the risk of overfitting is much less, we don't even need to regularize. So typically, the problems that we have when training models over the original features disappear in terms of calibration. Of course, we can't improve over the min DCF with this approach, but we can at least bring so the min DCF is controlled by the original model, but we can bring the actual DCF close to the mean with this method. Then the second scenario that happens in practice, we have miscalibration due to mismatch between the training and evaluation population, which means we don't have exactly samples taken from the field, but we have something that is similar that allows us to train models that will perform reasonably well. But this reasonably well means that since there is mismatch between train and the eval data, it means that this will cause us some errors due to the mismatch, due to the fact that the recognizer is not optimal. So the recognizer, if there is this mismatch, may learn to do what? To separate the training classes well. But then imagine that my test samples are a bit shifted with respect to the original samples. There will be some mistakes due to the classifier. But there may be some mistakes that can be compensated, at least partially, by changing also the threshold. So some of these error may manifest itself as miscalibration. And it can actually be quite a lot what you lose for miscalibration in this case. Of course, there is something that you can't recover with calibration because the model itself is trained on mismatched data. But there is something, but the error that you incur because of this mismatch is partially unrecoverable because it would degrade our mean DCF, but partially recoverable because it also introduces miscalibration error. So we can at least try to compensate miscalibration. How? Well, in this case, also calibration to be effective needs to be trained on data that is close to the evaluation data. So how do we solve the problem? Well, we need in this case to collect data similar to the evaluation data, so the application data. So this seems like cheating. I said, I have a mismatch. To compensate the mismatch, I collect the data in a way that the data that I collect do not present the mismatch anymore. So why can't I do that directly to train the original classifier? Well, the reason is that to train the original classifier, typically I need much more data than I need to train a calibration model. So that means that if I can afford to collect few data, additional data that are similar to the application data, then I can use those to improve my calibration. I will not improve mean DCF because I'm not retraining the full chain, but at least I can compensate some of the loss due to miscalibration. Of course, if I can afford to collect loss of data, then I would be better training my model directly on the matching data. So you can imagine that I have training data that has some mismatch with respect to the evaluation, and this will give me a recognizer that has some performance, let's say 0.2 DCF mean, and an actual that is 0.4. Then if I can collect a small amount of calibration data that is similar to the application, similar to this, then I can maybe bring this 0.4 close to 0.2. Of course, if I'm able to collect lots of data that is similar to the application, then I will not use this recognizer anymore. I will train a new recognizer that will also improve my mean DCF. So in this case, maybe my mean DCF will go down and my active DCF also will go further down. The difference is that the calibration needs this dataset to be much, much smaller because we're training a very simple model, a linear transformation with 2 parameters. So it's less expensive to collect few data than to collect lots of data. And if we use generative model, we don't see that, but we can even do away with the labels of this training data in some scenarios. So we may even be able to train a good calibration model even if for this calibration data we don't have the labels. And you can imagine that collecting unlabeled data is easier. For example, if I want to collect in our field with speaker recognition, so you need to recognize people from the voice. Collecting labeled data means that you need to have audio files with the name of the person. Unlabeled data is just audio files. So you can imagine that if you go to YouTube, it's easy to collect tons of unlabeled data. You don't know who's speaking, but you know that somebody is speaking. If you need to label them, it means that you need to take every file, audio, see who's speaking there, and put in the name. So collecting the labeled data is much more expensive. Then whether it's legal to download all the data on YouTube, that's another question. But up to some point, I think it was a gray area, so you can find data sets that were collected in this way. So people were doing that. So I don't know whether that was legal or not, but for sure people at some point were doing that for research, because there were data sets built in that way. In any case, unlabeled data is less expensive to acquire. For our project, we are in the first scenario. We don't have mismatch because we don't have the strength to address this mismatch further, so we keep it simple. So we are, sorry, in the first scenario, so the miscalibration is typically due to the classifier issues or overfitting, or, as we have seen, over-regularization for logistic regression models. Okay, now, problem that we need to address is, if we follow the strategy we have set up to now, let me just check the time because I want to finish everything today. Now our training set gets partitioned into 3 parts. If we want everything to be unbiased, we shouldn't test our calibration model on the same data that it was trained. So we can't train the calibration model here and test it on the validation set, because they would be evaluating a model on the same data that it was trained. In this case, it's the calibration model, but they would be evaluating the calibration model on the same data that it was trained. And of course, we can't train the calibration model on the data that was used to train the model, because the scores that I would obtain from my recognizer for this data have nothing to do with the scores that I would obtain for unseen data. For example, for models like SVM, for the model data, you would obtain very good classification, which may not generalize to unseen data. Which means that if I were to do what? Take this model training data, compute the scores for this, and then train the calibration model on these scores, then this model would not be a good model for the application scores, because the application scores are scores of samples that I've never seen. So the calibration model should be trained using samples that I've not used to train the model. And on the other hand, if I want to evaluate the validation, the calibration, I cannot use the same data that I trained the calibration model on, which means that this validation data, I can use it only for one thing. So how do? We split everything into 3 partitions. We train the model. The calibration trained data is data that we use to score the model, and the scores of these are the features that we use to train the calibration model. So here we would train the recognizer. Here we would compute the score for these calibration samples using the recognizer. This would give us the calibration model. Then with the calibration model, here we would compute the calibrated scores for these features and compute our ACT DCF over this validation set. Issue, we are splitting more and more our training data. If we had 1,000 samples here, now, no matter how we split, any split of this data set, there will be one of these sets that has no more than 1/3 of the samples. No matter how we split, one of the sets will have necessarily a number of samples lower than 1/3, lower or equal than 1/3. Which means that we had originally lots of data, and now the data is becoming less and less for each part. How can we address this? Well, we will see how to address this. Let's see, before we see that, just one more thing, how we will do the splitting in the laboratory. Now, in the laboratory, up to now, you were splitting into parts. So you were splitting model training and a validation set. Now, for the remaining of the laboratory, we will keep fixed the model training so that you don't need to retrain the model. Remember that in the laboratory, I was asking you to save the scores of the validation set. We will do all we need to do on the calibration using this data. So essentially, that means that we will take our current validation set and we will split that set into 2 more partitions. This allows us to keep our models as they are, because we don't need to train models anymore, because the training data, the training portion, the model training portion of the data remains the same. For the calibration, we will do all our analysis using what you are using now as validation set, which means that this validation set will need to be split at least into two partitions. One to train the calibration and one to compute the effectiveness of our calibration approach. Problem, I don't remember how many we had, but if I remember right, this was 1/3 of the data set, right? The validation in the project. If I remember right. Which means that you had 2,000 samples. Now, if we further split that into two parts, well, if we split evening, that's 1,000, 1,000. If we split unevenly, then I would say let's give this time 1/3 for the training, because the model is simple to train, so we don't need lots of score. And let's keep 2/3 for validation so that we can measure the accuracy, the metric in a more robust way. But we may also decide to do the opposite. In any case, you see that one of the datasets will become, if I want one of the datasets to be large, the other one needs to be small. Obviously, what I would like to have is to have both datasets large, because I would like to have a robust model and a robust evaluation of the model. Now, this is something that happens often. We have to split our data. The more we split our data, the smaller the sets that we obtain. What we did up to now was, okay, let's split the data into parts, and then use one part for training and the other for evaluation. Now, before we see the last topic of the course, the fusion, let's see a different approach that you may have already seen. Have you already talked about cross-validation in previous courses? Okay, so can I go fast on this part? Or? Okay, I will go not too fast. A way to reuse the data in a way that allows us to virtually use all the data, both for training and for validation. Let's ignore for the moment whether this is a calibration problem or what we were doing in the previous laboratories. Let's just say we have one data set which contains training data that we want to split into two parts. One will be used to train a model, and the other to validate the model. This could be what you were doing in the laboratories up to now. This could be what we will do for the calibration part in the last laboratory. In any case, we have originally we have one training set split in two, and for the calibration, we also have one data set that is split in two, one for training and one for validation. Then we will see how we can actually apply to a three-set partitioning, but we will see that as a side note. So up to now, we were doing split, train the model, and validate. What we will do now is see a way that is called K-fold that allows us to essentially use all the data, both for training the model and for validating its performance. Let me see if there is something here. No. K-fold works in this way. Rather than splitting our dataset into two uneven partitions, so one that is typically large and the other small, as we did, 2/3 for training and 1/3 for test, we split our dataset into K partitions. Here I've shown the partitions are unevenly because maybe the dataset is cannot be perfectly divided by K, but we will try to do all these partitions more or less with the same size. So with the same size up to what the dataset permits. So here we have one fold with one additional data because 10 cannot be divided by 9. But if we had 1,000, we would do 333, 333, and 334. In a way that if we have lots of data, it can be achieved by simply taking random the samples, but in a way that each fold more or less contains samples with the same characteristics of the original data set. What does it mean? It means that if I have one sample of the true class for every 3 samples of the false class, then each fold will try to mimic the same proportion. So each fold will have 1 sample of the true class for every 3 samples of the other class. If there are subgroups that I know in this training set, so for example, speaker identification, I need to split persons. There are some males, there are some females. Now, these have characteristics that are biologically different. So the voice of males is different from the voice of females. I will try to keep the same proportions of male and female in each fold. So I will try to preserve the characteristics of the data. If I have lots of data, this can be on average preserved by simply taking randomly the samples. I need to pay attention if my data set was not that big that randomly sampling may give me very unbalanced results. But for example, for the project data, we can just use random sampling to do this. Now, what is the idea here is, now we have 3 data sets. We can use these data sets to do what? To try to train several models. How? Each time we take 2 of these data sets in the example, so k minus 1, in our case, 2 data sets. We use this to train our model, and then we use the additional fold as a validation fold. So for example, we start training a model with fold 2 and 3, and we use fold 1 as validation. Then we train model with fold 1 and 3, and we use fold 2 as validation. And we repeat it for the last way. Of course, if we have k folds, we will train k models each time, leaving 1 fold out. So 1, 2, 3, 4, 5 will be the fold that I leave out of the training that I will use for validation. And I will train using all the remaining samples. What does this give me? Well, ideally, these models are trained with data that is similar. So ideally, I can imagine that these models will behave in a similar way. So for example, if I try to apply this approach with an SVM, I will obtain 3 SVM that will not behave very differently. So I can then take the scores produced by these 3 models, put them together, and evaluate them as if they were created by a single recognizer. Of course, there are some issues. These recognizers are not exactly the same. In theory, if we have infinite amount of data, then these models will converge to the same thing, because they would be optimal for an infinite amount of data. I would get the decisions that optimize the distribution, the average error. And in that case, the average error would be the same for all the models if the samples were a lot. So we can, as a first approximation, imagine that these models are similar, so we can take all the scores as if they were produced by a single model. We put them together, and then we evaluate our cost. Notice that I said we first put them together, and then we evaluate. So it's important that we evaluate over the whole set of scores. We will not compute mean DCF of S1, and then average it with mean DCF of S2, etc. This would be wrong. I will explain why in a moment. So we put them together, we treat them as if they were created by a single classifier, and we evaluate them. Of course, the models that we train must be trained with the same setup. So same preprocessing, same values of the hyperparameters, etc. Why? Because we're doing this for validating the model. So we want typically to compare different models and to see which one is better. We're not doing validation just because we would like to waste computational power. So the idea here is we'll try SVM with C equal to 1 and see how it performs. So train k SVMs with C equal to 1. Then I will try k SVM with C equal to 10. Each will produce scores. Then I will put together the scores of this SVM and evaluate them. This will give me what? Act DCF of SVM with C equal 1. then an ACT DCF of SVM with C equal 10, or mean if we are doing mean DCF. And then I can use these numbers to decide which is the best model, which is the best value for the hyperparameter. Is it C equal to 1? Is it C equal to 10? And then from that, I decide what is the values of the hyperparameters. Or if I am comparing SVM versus logistic regression, I can decide SVM works better than logistic regression for this task. So I can use it to compare models or to estimate as parameters as we were doing up to now with the validation set. What did I gain? Well, each model is trained with lots of data. The more the number of faults, the more the data that I have to train each model. And if you look here, all the data are also used to compute scores. So the score, the validation set, so the set over which I compute my metric has a size equal to the original training set. So all the training set samples are at some point used to train a model, and all the training set samples are also used to validate the model. But in a way that is not biased, because whenever I score a sample, it's scored with a model that has not seen that sample during training. So I'm not introducing a bias. Of course, I'm introducing some slight issues, some slight errors, because all these models will not be exactly similar, will not be exactly the same. So also the dynamics of these scores may not be exactly the same. So when I pull the scores, I may not have a unbiased estimate of how a single model, which we didn't introduce yet, would work on the validation set. And the second problem is, once I've done my selection, so for example, I decided to use SVM with C equal to 1, now I have K models, which one should I use for my application? If I use the first one, then the numbers that I evaluated are not 100% correct, because they take into account also the other two models. Which model should I use? Well, I can't compare the DCF of these three models, because each of these is a different validation set. So if I try to compute mean DCF of the first, compare it with the second, and compare it with the third, I don't know. Let's say the first has lowest DCF. Is it because that's the best model for my task, or because in the first fault I put samples that are easier to classify? Remember that there are samples that are easier to classify and samples that are more difficult. So for example, maybe this is my data set, and the first fault contains these samples. So for the first fault, whatever model I use, I will do very low DCF. That's not because the model trained with the other data is better, because this fault has data that is easier to classify. So I cannot compare the DCF of this. So which model should I use among these? The answer is none of those. Why were we doing models, all this type? We were doing it to decide that SVM with C equal 1 was the best performing model. Once we have decided that, do we still need the validation set at all? No, we already made all the decisions that we use the validation set for. So the last step is we will now fix the hyperparameters for the model that we have selected. So for example, we have compared logistic regression and SVM. For the SVM, we have decided that C equal to 1 is the best. For logistic regression, the lambda equal to 0.5 is the best. And then we have decided that SVM is better than logistic regression. So our final model will be SVM with C equal to 1. We take our training set, now the full training set, and we train a new SVM, now with all the data, using the hyperparameters that we have estimated. Now, of course, this model will be different from all the models that we have trained before, so our decisions may not be optimal anymore for this model, but if the faults are small enough, all these sub-models will be close as well to the one trained on everything. So if these sets are small, you can imagine that each model I trained was corresponding to removing one of these faults from the training set, because that was used for validation. If the faults are a lot, so they contain few data, then if I remove a fault that is small, it will not change significantly the characteristics of my dataset. Which means that typically the final model will have similar characteristics as the original, the ones that I will use to make my decisions. And this is the model that I will use for my application. Now, as we said, an issue of this process is that it's true that it works well when the faults are small, because the larger the faults, the fewer faults I have, the more each model that I train during the cross-validation step will differ from the final one. And the models that I train will also differ between themselves. So they will be different between themselves. So ideally, I can bring this process to the extreme, and rather than split my dataset into k faults, if I have n samples, I will fix k equal to n. Of course, now you may ask, if I have a single fault, how can I have this fault reflect the characteristics of the training set? Of course, it does not. What we said before, each fault should reflect the characteristics of the training set, is valid when I have few faults. Why? Because I want then the training set of the single models, the reduced training set, to be similar to the original one. So what matters is when I remove one fault, that what remains as the same characteristics as the original dataset. So if I have 3 faults, you can imagine that if I remove one, I'm removing lots of data. So I need to ensure that the other 2 represent the same characteristics of the training set, because this will be used for training. If I have k equal to n, what does it mean? It means that each time I will remove a single pattern. Implicitly, the remaining data will have characteristics that are very similar to the original training set, because I removed only a single sample. Removing only a single sample is the best we can do to ensure that all these models are similar. If all these models are trained with the same data except one sample that will differ, then we can imagine that the models will be very similar among themselves. And also, the final model trained with all the data will be similar to those n models that I trained. So the characteristics that I need to ensure that this approach works and brings me close to the optimal hyperparameters and perform close to optimal model selection is that the faults are very small. The problem is when k is large, then what happens? That we need to train many more models. If k is equal to n, we need to train n SVM, each with n minus 1 samples. So that gets expensive. That means for your data set, if we were to do this for training SVMs, you have 6,000 patterns, you will need to train 6,000 SVM. And for each of these SVM, you will need to train all the hyperparameters that you need to optimize for, So you would train for all the values of C, 6,000 SVMs. So you can imagine that this is infeasible. So how do we escape from this? We need to select k as large as we can afford. The larger the k, the better our analysis, of course, as large as we can afford, knowing that if it's larger, our analysis will be more robust, but it will take longer. If k is smaller, our conclusions may be less reliable and may even lead us to suboptimal results, but things can be evaluated in a much faster way. So it's a trade-off between what you can afford to do. The more you can afford, the better typically your results will be. For us, I think we will do it on the calibration part with k equal to, I think, 5. I have to check the laboratory. Now, of course, this can be done for training the model. So what we were doing up to now, apply it on the training set to do training and validation. We will not do this because they would require too much time. So for the model training part, we will stick with the split that we have done, which we'll also call single fault model, because we we have a single fold that is used for validation and another fold that is taken out from the training set, and we fix that forever. But for this last partition, for the calibration part, we will use the k-fold approach and compare it with the single fold approach just for the calibration model. So what we will do in the lab, we will take the calibration scores of what was before the validation data. This will be a data set on its own that we will need to use to learn the calibration transformation and validate it. We will try both a single split approach as we did before, but we will also try a k-fold approach where we split this data in k folds. The models here are very fast to train because they are just one-dimensional logistic regression. So training the k models on this problem is actually not that expensive. Okay. Final thing that I don't know whether it was before or afterwards. Pay attention that, as I said before, when you evaluate, you need to first pull the scores and then compute the metric. For some metrics, you could compute the metric on the different faults and then average those if the number of samples of the faults is the same, but that applies only to some metrics which have some properties. For example, mean DCF would not work, because if you were to compute separately the mean DCF on these faults, even assuming they have the same size, each time you would find a threshold that is optimal for that fault. While if you compute a mean DCF over everything, that is what mimics what you want to do, you will have a single threshold for all the scores. So the results will change. Your mean DCF estimated over the sample, over the singles dataset and average will be over optimistic. Imagine you have a k-fold with n equal to 1, with k equal to n, which is also called leave one out because we leave one training samples out from the training set. Then each of these blocks will contain one score. If you were to compute the mean DCF on a dataset with one score, what would be the mean DCF? If I have only one score and I can optimize the threshold to optimize the classification for that score, what would I do? I would have a mean DCF of 0, because if it's from the false class, I have a single score. If it's from the false class, I will put the threshold above it. If it's from the true class, I can put the threshold below it. If I can optimize a threshold for each fold, in each fold I have a single score, so I will have an optimal threshold. So with the leave one out, if I were to compute mean DCF and then average, the result will be 0 regardless of what the classifier can do, which shows that this is not the correct approach. There is nothing much to discuss. If everything I do gives me 0 mean DCF, there is something wrong. So you need to first pull the scores together, put them in a single array, essentially, and then evaluate them as if they were the output of a single classifier. Which also introduces a problem that will give you slightly worse than what you can probably do with the final model, but at least it's not being overconfident. In the worst case, it's a bit underconfident, but having a bit underconfident, this metric evaluation is much better than having significantly overconfident metrics. Okay, questions on this part? Of course, we will do k-fold in, as we said, we will not apply k-fold to everything for us. We will keep the model training part as a single fold where we train the model and then we use the other sample as validation. We apply the k-fold to the validation to transform it in calibration training and calibration validation part. If you wanted to do everything jointly, you could extend the approach to work with, to apply k-fold to all the parts, so both model training, calibration, and validation. But I think this is not particularly interesting. If you ever need to do it, you have some reference here how to do it, but I will not really discuss this. Essentially, one possibility is to apply k-fold to the classifier. Then the classifier applying k-fold will give me a set of scores that is a set of scores for all the training set data, because that's the output of a k-fold approach applied to the training set. And then over those data, we'll reapply k-fold. So essentially, I will take a training set. With k-fold, I will be able to associate a score to each of the training set sample, because remember that k-false gives me a score for all the training set samples. Then I will use this as if it was a training set and reapply k-fold on this, typically reshuffling this so that the partitions are not the same, so that partitions get mixed between the two procedures. But we are not going to apply this because it's just for you to know that it's possible to do it, but it's something a bit beyond what we need. So you have here the results, the idea, but we don't need it. Here you have what I was saying, what we will do for the laboratory. Now, the last part that I want to discuss is how to combine the results of different classifiers. So imagine now you have trained your SVM with RBF, you will train your GMM, and you will find that these two both have good results and make, in many cases, they make the same mistakes. In some cases, they make different mistakes. How can we combine the results of these two classifiers? So we may have different models which have similar performance, but they make different kind of errors. And in some cases, we may even have models that perform much worse than others, but are able to extract some information that the other model does not see. So can we exploit this additional information to improve the performance of our classifier? Can we do that or not? Of course, the answer is yes, we can. Otherwise, we will not be here asking. Now, some simple strategies that you may, I don't know if you have already seen these kind of things, but you may have seen the simplest thing that you can do is, okay, have every classifier make its own prediction, and then let's try to combine them. If it's binary, I will have classifier 1 that says it's class true, classifier 2 that says it's class true, classifier 3 that says it's class false. So in this case, I may be tempted to say it's class true. Problem, many problems with this. First problem, what if I have only two classifiers? Or what if I have a number of classifiers such that there are two options that have the most voted options have the same value? Which one should I do? But even the worst is this. I have just two classifiers. Remember that the more classifiers I have, the more expensive my model becomes because I need to score all of those. So if I have just two, because I want to improve a bit, but I don't want this to cost too much, then I cannot apply this procedure at all. Then, another problem. We have that classifier 1 says true, classifier 2 says true, classifier 3 says false. But let's now be a bit more precise. We have an application with prior 0.5, so threshold 0. Classifier 1 says score equal to 0.1. Classifier 2 says score equal to 0.05. Classifier 3 says score equal to minus 3.5. What does it tell us? Well, if I were to look at a classifier, true, true, false. It's the same as before. But what is the strength? What is the class posterior probability in this case? Here it's close to 1/2. Let's put 3. Here it's even more close to 1/2. Here it's, for class 1, is much lower than 1/2. So if I say, this will say, the probability that it's class 1 is almost 1/2, but that's almost the same for class false. So that means I'm very unsure to which class this belongs. There is almost the same probability for both. A bit more for class 1, so if I have to decide, I will decide class 1. But the probability for the two are very close. The other says, there's no way this is from class 1. So imagine you have two people that says, well, I don't really know, it may be class 1, but I'm not really sure. Another people says, it may be class 1, but I'm also not very sure. And then somebody tells you, I'm an expert and I'm sure it's not from class 1. Who would you trust? You would ask ChatGPT, who says it from class 3. So you would trust the last one. So here you would say it's from class false, because the third classifier says, I'm sure, well, not almost, but let's make almost sure, let's put it minus 13, I'm almost sure that it's from class blue. The prior must be very, 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 very towards class 1 for me to change my idea. So I'm almost sure it's from class 2. So how can we combine the classifier when the classifier gives us score? Well, we may then imagine that we need to do something that takes into account these scores. Any suggestion on what we can do? Let's imagine we have 3 classifiers, which gives, for the same sample, 3 scores. So now these are 3 classifiers, not 3 samples. The classifier is 3, the sample is 1, and we have 3 scores. How can we combine those scores? So one option is average of these. Other options? The highest. Other options? Yes? Your linear combination of the 3. Other? Okay, there is 1/4 that is just sum them, that I will add. And let's now see who goes for this one. Well, you have to go for that one because you proposed it. So who goes for the highest? You. Linear combination, him, and the sum. Okay, all of these are, in some sense, correct and in some sense wrong. So the answer is, it depends. We will see that the one we will use is actually the last one. But let's see when they are correct and when they are wrong. Let's start with the sum that nobody proposed. Because the sum we can show is the correct thing to do when the scores provided by the different recognizer provides independent scores. What does it mean? Imagine that I have my feature vector, x, which contains 2 parts. Then recognizer 1 produces a score looking only at the first half of the features, and then recognizer 2 produces a score looking only at the second part of the features. And imagine that these 2 parts are independent, so the features can be considered independent. Let's call this part x plus and x minus, okay? Then, my complete model would be the density for x given h true divided the density for x given h false. That if I combine these two, will be, if they are independent, it's the density for h plus given h true times the density for x minus given h2 true, because if I assume the features are independent given the class labels, then the density for the whole thing can be factorized, and below the same. If I assume independence given the class, then I can also factorize what's below. Then I have R1 giving me a model for this, R2 giving a model for this. If I put the log in front, the result is log of the density for x plus given true, divided density for x minus given false, and then I have a product which becomes a sum of logarithm of the product. So what I get is this. Now, if I use the score of classifier R2 for this and the score for classifier R1, you can see that the result is the score for classifier 1 plus the score for classifier 2. So if the models produce well-calibrated log-likelihood ratios, and this well-calibrated log-likelihood ratio refer to information that is independently extracted from the features, maybe because they look at just part of the features, or they are even trained with different features for the same object. So for example, you have image recognition. One model is trained with the colors of the picture, the other with some other information that I extracted from the picture, so which is independent, then the sum is the correct result. In the forensic world, this would say that if we have to recognize and look at independent evidence, then the contribution of the evidence sum up together. If I have models that are independent and each one has some support for the hypothesis, the contribution of the two models will just add up. Of course, this is true if the models are independent. Let's imagine, for example, that I have R1 and R2 that are the same model R. Let's imagine that R1 gives the score S, and R2, of course, gives the score S for the sample X. So for sample X, we get score S, for example, 10. And that the model is well calibrated. So this 10 is a well calibrated score for the sample. If I take the sum of the two, my sum score is 20. But if 10 was well calibrated score, then 20 is not a well calibrated score for the model anymore. So the sum will break when the models are not independent. In that case, when there is complete dependence, the average would be correct. I would be averaging always the same value, though. So the average would be correct when the models are the same, which makes them useless in any case. But if they are strongly correlated, then the average is a more close approximation to what I wanted to achieve. The highest has some issues that essentially ignores the contributions of weak classifiers, and then again, there is some issue when I have what? If one is in favor of 10 and the other is in favor, and then I have 4 classifiers that are weakly in favor of the other class, overall I have a strong, and imagine these are independent, then I have a strong evidence towards class false, but I would select class true. So that's not, again, the best thing. So we said average when they are strongly classifier related, some where they are almost independent. In both cases, we have a combination of the 3 scores. So let's say that rather than relying on measuring how much the combination is, we let the transformation be parametric, and then we use a model to estimate how much weight we should give to the different classifiers. This will allow us, if they are independent, the model will realize that it needs to obtain the best results to put a 1 there. If they are the same classifier, it will just put an average weight, or just select 1 because the results is the same. The scores that I'm summing are the same. So whether I sum 3 scores with weight 1/2, or I sum the first with weight 1 and the other with weight 0, it's the same results when the scores are the same. And in a way that gives us a way to map the different scores to a single fusion score. Of course, we can make this more complex, but let's stick with a simple model where we add the different scores. How can we learn the parameters of this model? Some suggestions? Remember when we were doing calibration, what we were saying. The calibrated score, we model it, well, in this way. Then this gamma was the beta that we estimated minus, etc. Okay. But in any case, and then we said, let's learn this, or actually this was indirectly learned through the parameter of a logistic regression model using a prior weighted logistic regression. So what can we do now? We want to learn a mapping so that this is a score that represents the combination of the original scores, and hopefully is also well calibrated, because we want to preserve well calibration. What can we do? We can train a prior weighted logistic regression to learn the weights. If I These are the scores for a single sample. So we are here looking at a sample. So here the index refers to the classifier. We have M classifiers, R1 through Rm, each producing a score for a sample X. If we take the M scores and put them in a vector, and we call this vector S, and we put the weights in a vector as well, and we call the vector alpha, then the fusion score is alpha transpose S plus gamma. Is it different from W transpose X plus B? If we call S, rather than call it S, we call it X. If this, we don't call it alpha, we call it W, and this, we don't call it gamma, we call it B, we have the model of logistic regression for the features. The score is a linear combination of the features. So we can, and we said that logistic regression, if it's trained with lots of data and not too large features, will provide scores that are typically well calibrated. So we can learn these model parameters by logistic regression, and in particular, prior weighted logistic regression. Of course, if we train the prior weighted logistic regression as we did now, this gamma will contain also the contribution of the empirical prior of the training set. So if we want this to be well calibrated, we will need to take our fused score and remove the prior log odds that we used for training. That's as usual for the prior weighted logistic regression. That's exactly as we did for calibration. So the idea here is the same. We do the same thing as we did for calibration, but for calibration, we had what? For each sample, we were computing a single uncalibrated score. Then using these as if they were training set, we trained a prior weighted logistic regression that gave us a single value alpha and a value beta. Then our calibrated score will be the uncalibrated times alpha plus beta minus the empirical prior log odds, or since it's prior weighted logistic regression, this would be the actual prior that I was using during training. And for fusion will be the same. We have a set of x1 through xm validation scores, the same that we were using here. For each of them, now we have, n samples. We have m classifiers. So for each of these, we will have a vector of scores. And m, sn1 through snm. So we will have a matrix of score now. We will treat these as samples. We'll learn a prior weighted logistic regression model over these. These are matrix of samples. Each column is a vector of scores for the m classifiers for the corresponding sample. The prior weighted will give us a, let's call alpha and beta. And then our final model will be, when we want to apply it, we will have a test sample xt. We compute our uncalibrated scores with the recognizers, T1 up to xtm. And then let's call this, S. We call this st, and our final score, the fused score, will be what? If we learn the prior weighted logistic regression using the model that we said, which embeds the weights here, the fused score will be alpha transpose st plus beta minus the prior log odd. Again, the empirical prior, if I use the data set as it is, or the prior that I trained the model for, if I specify the application. This is my gamma. All this part is gamma. And this alpha are the weights that I give to the different systems. The only thing that we need to pay attention is, again, to transform the score in a log-like ratio. So we can reuse the logistic regression as it is, but this time, rather than passing an array which contains a single score per sample, it will contain a vector of scores per each sample. And we will learn the parameters of a weighted combination of the scores. The final score will hopefully will be well calibrated when these scores are not a lot, but typically you don't fuse hundreds of systems. You may fuse few systems, maybe 10 systems. When you get to 15, you're already fusing lots of systems. There is typically a diminishing returns effect. So if this is the mean DCF with the best system, when I add the second one, I may improve. Then I may improve with the third one. With the fourth one, I may improve. But then the improvement, if I keep adding different systems, will at some point stop. So typically, we don't go over few units. So 5, 6, 3, 4, 5. You may get to 10, 15 when you're already overfusing models. But when you want to squeeze everything you can out of what you have. But typically, the size of this will be few units. So 5, 3, 4, 5. So we still are not getting into the overfitting issues of having a large feature space for training the prior weighted model. So the result is a fuse score that typically will also be well calibrated for what? For the application we train for, but as we said for calibration, typically calibration effects will extend to applications that are not too different, and in some cases even to applications that are very different, as you will see in the laboratory part. And of course, you can consider that if I have a single system, a single recognizer, this is exactly the calibration model we introduced yesterday. So this can be seen as an extension of the calibration for multiple systems. If I do all the process with a single system, I'm doing exactly the calibration model that we discussed yesterday. So I have a single score that gets scaled, to which I add a bias, and the training would be the same. Okay, questions? Okay, last word. For multiclass problem, it becomes much more complex, first of all, because we don't have a single threshold anymore. So even defining how we measure miscalibration error becomes a bit more complex, because it's not well defined how I would select an optimal decisions on the evaluation from the scores of the classifiers. There are some ways, but again, we are not going to introduce them here. But know that even in the multiclass case, things become more complex, but it's possible to, in some way, measure the contribution of miscalibration with some additional assumptions on what you are actually measuring, which is much less evident than in the binary case, so that's why we stop with the binary case. But it can be extended to multiclass, and we can apply similar procedures to calibrate multiclass classifiers. In this case, typically, we will use multiclass models like multiclass logistic regression to again train linear combinations of the scores for multiclass problems. So typically in a multiclass problem, a score is already a vector on its own because we have a score vector, one score per class. So we will make linear transformation of these score vectors in a way that allows us to improve the overall performance of our model. So, for example, the bias risk for our models. Okay, that's all I have to say here. Are there questions? Okay, then if there are no questions, I will do two things. One, since we were a bit late with the GMM, yesterday I introduced it in the laboratory, but now I have time to say what I said yesterday to the whole class. I took like 10 minutes, so it's better so we can all see the things together. For those who are from the quantum computing course or long course, these last 10 minutes are not part of the program. And the other thing, but I will discuss the content next Friday, online you have examples of questions. They are actually there from last week already. of both the theory and programming part. So programming project, it's not all programming. Some part you don't have to program at all. There may be some questions on programming and some questions on the project part of the laboratory. So you have examples of all. So for example, these are the non-programming project questions, and these are the programming project questions, which may look long, but they are not that. It's much, the question is much more, is much longer than the answer. So it takes more time to, if you did it, it takes more time to read the question than to write the answer. And you can see if there is, you will not have any material, but you see if there is something that you need, I will provide you some prototype and some documentation of the function that you may need, that you may not remember from. So you don't need to remember the library functions by heart. Maybe the things that we use most, yes, but I will give you some additional stuff if required. Then next week we have Thursday laboratory with you, and then on Friday we'll have laboratory with the other course, and then the last class, which on the portal I saw it's written wrongly. I will correct it if I remember this week. It's written wrongly in the sense that here it says again 30 May, but it's actually 6th of June, because 30th of May was today. So this is 6th of June, of course, where you will be questions and answers on what we have seen on the projects if you have, and I will discuss a bit more these examples of exams. Then, for what remains, let's exploit these 10 minutes so you can have more time then for the laboratory, because you have questions for the theory part, we have finished. We need to say a couple of more things on the GMM, but these couple of more things are actually how we use it, so they are also related to the laboratory. You will see them in the laboratory in any case today, but I wanted to say a couple of words on that. So I take this time so that for the labs you have more time to actually do the laboratory. Okay, what was to be seen was how to, well, we stopped at how to use the GMM. Then we said how to prove that our EM algorithm converges. It will not be part of the exam because we don't have time to see it, so I will skip it. And in any case, I would have not asked for that part of the exam in any case. I don't say it in advance, otherwise you don't listen, but that part is never part of the exam also for the previous years. So you're not really gaining anything for the exam part, unfortunately for you. Let's see the part that I will ask. Of course, I will ask, we didn't say it's called EM algorithm, so what I will ask is, I may ask to apply the EM algorithm, which is the algorithm that we saw, so you need to know that it's called EM. And the expectation step is, this comes from expectation maximization. We don't explain why it's called that way, but the expectation step is the step where we essentially compute class posterior probabilities. It's not exactly that. It's the step where we compute this, and then we write down the function that we need to optimize, but since we didn't see everything for us, the step is where we compute the class posterior probabilities, and then following the procedure that we just saw informally last time, in the M step, we maximize a function that we didn't see, whose optimal is exactly the procedure that we saw. So the M step will iterate through what? Start from some parameters, compute class posterior parameters, probabilities, cluster posterior probability for all samples with those parameters that we have seen last week how to do. So we saw this part. We didn't see the EM algorithm in general, but we saw how to do it. And then, using this, compute the cluster, the GMM parameters for iteration 1. And then repeat using this expression. These expressions are reported in these slides, but are the same that we were already seeing. The mean is a weighted mean of the samples, the covariance is a weighted covariance matrix, and the weight is the fraction of points assigned to the cluster divided the total number of points. These are the same expression that we saw in the part that is part of the exam before we did the example. So at the same expression we saw here. Mean covariance matrix. Remember that NC is equal to NC is equal to the sum over I of gamma Ci. So here it's written NC, but it's the same thing as this is NC. So it's the same expression, and then for the weights, again, the same expression written in terms of NC and N rather than gammas, but it's the same exact value. Now, we said quickly how to use it for classification. Let's see that in a bit more detail. How we will use it for classification, essentially, in a similar way as the MVG, but with the MVG we're doing what? We're training a Gaussian per class. So we would have Gaussian 1 and Gaussian 2, and then for a generic multiclass problem, we would compute the class posterior as what? Prior for class C, let's say C is equal to 1. Prior for class 1, the Gaussian for that class divided what? The marginal, that is the sum over all classes of the prior for that class times the Gaussian for that class. This is the class conditional density for the given class. For the GMM, what we will do, the same thing. Just rather than fitting a Gaussian per class, we'll now fit a GMM, possibly with different number of Gaussians, to each class. So this will be GMM 1, so with its own set of means, covariance matrices, and weights. So the full set, here I will have mean 1, mean 2, and mean 3 for the GMM 1. Then covariance matrix 1, 2, and 3 for the GMM 1, and the weights for the same components. And then I will have mu 1 and mu 2 for the second GMM, sigma 1 and sigma 2 for the second GMM. And then I can do the same as we did before. For the multiclass, I will compute class posterior probabilities. How? Let's imagine I want class 1. I will have prior for class 1 times the class conditional density for class 1. But the class conditional density is now what? It's GMM for X with the parameters of, let's do it in red since the class 1 is red. It's pi 1 times GMM of class 1. But GMM of class 1 is what? It's pi 1 times sum over the components of the GMM, which are 3 for class 1, of W, let's put the space that we need, W1I, component I of GMM1, times the Gaussian I1. And then, of course, below, I have the sum over all components of pi c times the GMM for class C. So I have sum over classes, prior of the class, GMM for the density for that class. Okay, so it looks difficult, but once you pack it into functions we will see in the laboratory, essentially it's density for the GMM of class C multiplied by the prior for class C, everything added. And of course, if it's a two-class problem, I can compute a log-likelihood ratio as logarithm of GMM for class 1 divided GMM for class 0. So I will have logarithm of the sum of Wi1 normal of X mu I1 sigma I1 divided the sum. Now here I goes from 1 to 2 because the second only has 2 in this case components. So the second GMM in this case is only 2 components. And then this will be the log-like ratio that I will use. So there is nothing different. The only difference is that instead of having normal here, I have GMM here that was trained for a given class. Now, another thing that I want to say is how to use this for open set. The GMM gives us a first way to address open set classification. How? Well, open set we saw could be cast as a closed set with an additional class that is none of the other classes. The problem is that typically open set has the problem that the none of the other classes is complex. So typically, imagine this is a speaker identification problem. This is person A, B, so, and these are any other possible person in the world. So having a good model of this is difficult. There may be cases where I can collect data that represents reasonably well this none of the above class, but again, collecting labeled data for that class is difficult. If I have unlabeled data, I can still try to do something with a GMM. How? Well, maybe I can fit a model where I use a single Gaussian because that's easy to classify for the samples of class A and B, and then I will use a GMM to try to model the density of the none of the above class. The none of the above of the other class is very heterogeneous because it contains many different subclusters, but we have seen that the GMM is able to partition our data into subclusters which can be considered homogeneous and modeled with a single component. So I can try to use a GMM to get a reasonable estimate of the none of the other class. Of course, this requires that we have at least unlabeled samples for the none of the other class, so we should know that they are none of the other, but we shouldn't know which kind of other possibilities they are. So for example, I know this is Alice, I know this is Bob, and I know these are neither Alice or Bob, but is a very huge collection of other people. I don't know the people inside, but I know that there are many other people. Then I can use a GMM to try to model that. Of course, I may have issues with calibration because the none of the above class, even if it's modeled by GMM, is very heterogeneous, typically large dimensional. So my model for that class will not be that precise. So typically when I use this kind of approach for the modeling none of the above class, I will need to do something about calibration at the end. But at least it's a first way to address this task that we said at the beginning of the course. We are not able to address it properly. We will be able to start seeing a possible way only at the end of the course. Questions? Okay, if there are no questions, well, there is one more thing. I think I can take another 5 minutes to say it to the whole class before we start the lab. Otherwise, you will need to hear it in the laboratory, so it will not change much. Let me take another 5 minutes. In the laboratory, okay, consider this laboratory already, because we will see that in the laboratory as well. In the laboratory, we will see an optional part with different variations of the model. The model that we are seeing now has a Gaussian components whose covariance matrix is full. Of course, if we want to reduce the number of parameters, we can again adopt models where the covariance matrix of the components is diagonal. In this case, my GMM will be based on components that are aligned with the principal axis. Or notice that in contrast with, and this is the only thing that I want to say, in contrast with the diagonal Gaussian model, having Gaussian diagonal components in the GMM is not the naive Bayes assumption. Naive Bayes assumes that features are independent. If I have two Gaussian components for the same GMM, which have diagonal covariance matrix, this does not correspond to independence on the features. Imagine you have a configuration like this. If you know that one component, it means that points are either points that have values close to 2, 2 or close to 1, 1. These components are diagonal, but overall there is a strong correlation between the two features. If one vector has a component, a first component that is 2, then there is a high chance that also the other component is 2. That's what the model is saying. This is a region of high density samples. So most of the samples that have a second component, a first component 2, will also have a second component that is also 2. So the two components are strongly correlated. Indeed, if I were to look at the correlation matrix of this would be the shape of the correlation matrix overall. But you see that the main model have diagonal components. So we can use diagonal components to make our parameters less, but that does not correspond to a naive Bayes assumption. So it's not diagonal equal naive Bayes. And the last thing that we can do, of course, we can also force all the components of a GMM to have the same covariance. We call this tied GMM. Notice that it's not the same as the tied MVG, because in the tied MVG, we are tying the covariance of the models of the different classes. Here we are tying the covariance of the components of a single GMM that represents a single class. So a different class may have a different tying where the covariance matrices are aligned in a different way, class 1, class 2. Tying here refers to all the components having the same covariance. Of course, we can create a model where the components for class 1 and the components for class 2 have the same covariance, but not with what we saw, because in that case, the M algorithm that we saw would not work anymore, because we cannot independently fit a GMM for each class. So, in the laboratory, you have optional part to try to train these two models that I suggest you try to do because it's very quick. I don't have anything other to say. If you want, you can read the rest of the slides which compare the models with what we saw before. Questions?